Black holes are one of the most fascinating phenomena in the universe, where gravity is so strong that even light cannot escape its grasp. However, that is not all there is to be intrigued about them. Black holes are not only mysterious, but also contain the potential to propel humanity to new heights in the exploration of the cosmos. Understanding how black holes function may even lead us to comprehend the origins of everything. The term black hole doesn't fully capture the essence of this phenomenon. When we talk about black holes, it's hard to classify them as an object or a celestial body like stars or planets. Black holes stand in a category of their own among the things that appear in the universe because they are utterly unique, so much so that we struggle to define them. To this day, the brightest minds of the world, past and present, are still grappling with interpreting this phenomenon. Why is that? First, we need to understand a basic concept about black holes, the event horizon. When we look at stars or planets, we see spherical bodies that give us the feeling that if we touch these spheres, we will encounter something like with Earth, we would find the atmosphere and then the ground. With the sun beyond the bright sphere, we would encounter the nuclear reactions in its core. For gas giant planets, the sphere would contain massive storms, fierce winds, and torrential rains composed of strange matter. With moons, it's mostly rock, or in some cases like Titan, an interesting atmosphere. But black holes are different. Black holes might have a spherical appearance like the other familiar spheres in the universe. But the surface of a black hole gives us no information. The concept of no information needs emphasis. The event horizon is not the atmosphere or the surface of a black hole. It's the last point where any event has any significance to humanity. Once crossed, gravity becomes so strong that nothing can return to our world. That's why beyond the event horizon, whatever happens is beyond our knowledge, which is why we cannot get any more information about it. Moreover, the massive gravity of black holes bends space-time to such an extreme that space around the black hole becomes distorted, forming the spherical appearance we often see in black holes. To answer what this distortion is, we need a bit of imagination. Imagine what happens when you fill a sink with water and then pull the plug. Water is drawn into the hole and twists into a vortex. Looking into the mouth of the vortex, you see water bending light in unusual ways. Similarly with black holes, but on a much grander scale, black holes bend space, causing light falling into it to be twisted like water into a vortex. The light we see around black holes is not because the black hole is emitting light. It's the light from behind the black hole that speed-eye is directing in front of it. This happens at every angle, light from above, below, and the sides gets refracted around the black hole. That's why the most common image we have of a black hole is a bright ring surrounding it, as if it is rings of light around itself. Gravitational lensing doesn't just occur with black holes, but also in regions with enough gravity to affect spine. This makes observing a universe harder, but does diminish its beauty. Now we understand what the exterior of a black hole looks like. But what about the inside? The event horizon is a point of no return. Once we cross it, we are forever within the black hole. Right, then how do we know what's inside a black hole? This question is, if we talk about the inside of a black hole as if describing a planet or a star, we have a clear understanding of what's inside. But the void here is that we cannot accurately describe it. We know that beyond the event horizon there's nothingness. The event horizon is not a cloud we can step through, hoping to find ground underneath. It can be seen, but in reality, it doesn't exist as a tangible object. It's still infinite space, but the difference is that gravity begins. Once fallen into a black hole, we fall endlessly until we reach the singularity. What is the singularity? It's the most special question of the century, and the largest puzzle humanity has ever encountered. When you find the key to unlock the door named singularity, we will step into a new world, a new horizon of understanding about science, about everything, and perhaps humanity will become a higher civilization just because of this grand discovery. Why is that? Because the singularity contains the question of the existence of everything. According to Einstein's theory of relativity, black holes are born when a massive star reaches the end of its life cycle. It compresses its nuclear core, synthesizing silicon into iron, and iron is the final form of matter. The core succumbs to gravity, crushing the star, resulting in a colossal supernova explosion. It gives birth to a black hole. Here begins a paradox. Before it was a black hole, it was a star. A black hole and a star have equivalent mass, but their properties are vastly different. The star also bends time and creates gravity around it, but not to the extreme extent of a black hole. The same mass, yet different gravitational effects. Why? The answer lies in the density of matter, or the specific mass of a black hole. The higher the density, the more compact and heavy the matter becomes. Why, it's why a kilogram of cotton and a kilogram of steel have the same mass but different volumes. All the matter of a star is now compressed into an infinitesimally small volume like a marble. This means the matter at the singularity is in a state that defies explanation, infinitely dense and creating infinite gravity. When we talk about infinity in cosmic science, it means we don't understand why it is so. Hence, singularity is declining. It is not a heavy marble that has the weight of a star. It's not a point at the center of a black hole. It is not a location within the black hole. More accurately, it is a moment in space-time from which nothing can escape. It's like tomorrow. We can move from east to west or north to south, but we cannot escape tomorrow's arrival. We don't know what it is or why it is so. But why is it the key to our law of knowledge? Everything they've known about physics falls apart in a singularity. No physical law can explain the existence of a singularity. Even if we compress matter, particles like protons and electrons still need to exist to form matter. But in the tiny and confined space of a singularity, even fundamental particles have no room to exist. So, how can a singularity exist? This is where Einstein's theory of relativity falls short. It describes gravity as a curvature of space-time, but it doesn't explain the extreme conditions at a singularity. Newton described gravity as a force, but didn't explain its origin. Similarly, Einstein's description of black holes as gravitational oddities doesn't explain why singularities exist. The existence of black holes and singularities pushed Einstein to delve into the quantum world, where particles smaller than electrons were used for calculations. Here we encounter a new gateway of knowledge. The quantum world and where we observe daily are not the same. When we see an object, we know where it is in space and can relate to the time we observe it. In contrast, in the quantum world, we can't predict where an electron will be at any given moment. The existence of an electron around an atom is described as a cloud of probability, not as a satellite with a fixed orbit around a nucleus like planets around a star. An atom comprises fundamental particles that make up the nucleus, while the space around the nucleus is filled with potential positions for an electron. The electron can exist anywhere within these potential positions, and whenever we check, we'll find an electron within that area. This cloud-like structure, a nucleus and potential electron cloud, more accurately describes an atom. But scientists face a problem when using the term particle. Particle or particulate refers to matter in the form of discrete units. Energy and matter are fundamentally the same, as E equals mc squared. This, light doesn't need mass, it merely requires energy. How, then, does light, which has no mass, move at the maximum speed in the universe? If it's a particle, it must have mass. If it's not a particle, how can it move? Quantum researchers realized the truth. Might in many things we call particles are really particles. They are products of quantum fields. Quantum field theory suggests that multiple quantum fields exist over space-time, allowing forces to interact and energy to transform into different particle forms. This allows light to exist as a wave of energy without needing to be a particle, which is why it can travel through the vast emptiness of space, where matter is scattered millions of miles apart. The discovery of quantum fields not only expanded our understanding of matter, but also gave us the opportunity to explore a world of particles in a quantum superposition state. where they simultaneously exist and do not exist, when independent state. The most famous example of this state is Security's cat, proposed by physicist Ernst Cordia to explain this concept. But what does this theory have to do with black holes? Humanity has spent decades studying the quantum world, identifying fundamental particles that make up basic forces and matter. The research into quantum theory has been so successful that, for the first time, we have a branch of hard science that has matured so quickly. We almost fully grasp the principles and laws governing fundamental particles, and how they operate in any given moment, all within the framework of Heisenberg's uncertainty principle. However, despite the successes of quantum science, it still has a gap. According to Einstein, anti energy are when matter impacts spin to create gravity. So do fundamental particles exert gravity? The answer should be yes, as they are energy inert to affect spin atom. But in reality, within the tiny space of fundamental particles, we cannot measure the curvature of spin using Singh's formulas. And why do they find this point of meaninglessness? In the singularity of a black hole, the place where Einstein's theory of relativity crumbles. Not because Einstein was wrong, but because that place belongs to quantum physics, and in the quantum world Einstein's physics become irrelevant. For this reason, scientists, including Einstein, dive on the quantum time to find a connection between the theory of relativity and quantum gravity, nor quantum nanodial. To this day, no scientist has exact equations or ideas to describe this profound concept. There are only two theories that most accurately approach quantum gravity still under research and debate: loop quantum gravity and string theory. Both have compelling arguments but also contain many gaps. Neither string theory nor loop quantum gravity has been universally accepted by the scientific community. There is still much work to be done to bring the truth to light. Although this is a rather dark and disappointing conclusion, it opens an incredibly fascinating and challenging path. With Newton's incomplete theory, we took humans to the moon. With Einstein's incomplete theory, we captured the first image of a black hole. So with an incomplete understanding of the existence of everything, both in the theory of relativity and quantum physics, why can't we make significant progress? You may not know now, we are sure that it will be a major leap for humanity, and it was our second piece about the story of black holes, about the structure of this phenomenon, and the difficulties scientists face when trying to define its singularity. If you enjoyed this video, don't forget to hit like, subscribe to our channel, and click the notification bell so you don't miss any future videos. Thank you for listening, and we'll see you next time for more exploration.